Today I'm going to be doing Andrei Karpathy's Zero to Hero, and I'm going to try it in C++. I have not used C++ much before. Let's get started.
Hello, my name is Andre, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we are going to start with a blank Jupyter notebook, and by the end of this lecture, we will define and train a neural net. And you'll get to see everything that goes on under the hood and exactly sort of how that works on an intuitive level. Now, specifically what I would like to do is I would like to take you through building of micrograd. Now, micrograd is this library that I released on GitHub about 2 years ago, but at the time I only uploaded the source code, and you'd have to go in by yourself and really figure out how it works. So in this lecture, I will take you through it step by step and kind of comment on all the pieces of it. So what is micrograd and why is it interesting? Good. Micrograd is basically an autograd engine. Autograd is short for automatic gradient. And really what it does is it implements backpropagation. Now, backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality of micrograd is, I think, best illustrated by an example. So if we just scroll down here, you'll see that micrograd basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are -4 and 2, but we are wrapping those values into this value object that we are going to build out as part of micrograd. So this value object will wrap.
The wrapping is pretty common. Then, for example, in PyTorch, torch.tensor is essentially doing the same thing as an entry point. Although in his case, instead of dealing with tensors, it looks like it's just single values, at least for now.
The numbers themselves. And then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of micrograd and the operations that it supports. So you can add two value objects, you can multiply them, you can raise them to a constant power, you can offset by 1, negate, squash at 0, square, divide by a constant, divide by it, etc. And so we're building out an expression graph with these two inputs A and B, and we're creating an output value of G. And micrograd will, in the background, build out this entire mathematical expression. So it will, for example, know that C is also a value. C was a result of an addition operation, and the child nodes of C are A and B, because and it will maintain pointers to A and B value objects. So we'll basically know exactly how all of this is laid out. And then not only can we do what we call the forward pass, where we actually look at the value of G, of course, that's pretty straightforward. We will access that using the .data attribute. And so the output of the forward pass, the value of G, is 24.7, it turns out. But the big deal is that we can also take this G value object and we can call .backward. And this will basically initialize backpropagation at the node G. And what backpropagation is going to do is it's going to start at G and it's going to go backwards through that expression graph and it's going to recursively apply the chain rule from calculus. And what that allows us to do then is we're going to evaluate basically the derivative of G with respect to all the internal nodes like E, D, and C, but also with respect to the inputs A and B. And then we can actually query this derivative of G with respect to A. For example, that's A.grad. In this case, it happens to be 138. And the derivative of G with respect to B, which also happens to be here, 645. And this derivative, we'll see soon, is very important information because it's telling us how A and B are affecting G through this mathematical expression. So in particular, A.grad is 138. So if we slightly nudge A and make it slightly larger, 138 is telling us that G will grow, and the slope of that growth is going to be 138. And the slope of growth of B is going to be 645. So that's going to tell us about how G will respond if A and B get tweaked a tiny amount in a positive direction. Okay. Now, you might be confused about what this expression is that we built out here. And this expression, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly
What's not a mathematical expression?
a bit less crazy even. Um, Neural networks are just a mathematical expression. They take the input data as an input, and they take the weights of a neural network as an input. And it's a mathematical expression, and the output are your predictions of your neural net, or the loss function. We'll see this in a bit. But basically, neural networks just happen to be a certain class of mathematical expressions. But backpropagation is actually significantly more general. It doesn't actually care about neural networks at all. It only cares about arbitrary mathematical expressions. And then we happen to use that machinery for training of neural network valued autograd engine. So it's working on the level of individual scalars like -4 and 2. And we're
Okay, so far for me, this part's been stuff I already know. So to make it a little more interesting, I think I'll do the scaffolding for the C++ part so that when he does get to the coding, I'm ready. Starting with how to set up a C++ project in VS Code, because why not? How it was starting up is just slow as hell. Oh yes, I will install the pre-release. 50 million installs. Yeah, sure, you can sign in using GitHub. I swear, every time I have to do this. What's up with this sign-in? Okay, there, that's better. After all that, I get the privilege of restarting to update. Well, I for sure have G++. Oh, okay, looks like creating a C++ project really is simple. Wait, what the hell? I'm running an emulated version? I had no idea. Okay, well, that's going. And what to call it? 0 to hero 1. Why not? What? It still thinks it's emulated? Screw it, this is a rabbit hole that I'm not going down right now. I can't tell if it's I like installing things or programming just has a lot of installing things or a bit of both. Oh, I should probably turn off Copilot. Okay.
We're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times, and it's just excessive. And so obviously you would never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations on those large arrays that allows us to take advantage of the parallelism in a computer. And all those operations can be done in parallel, and then the whole thing runs faster. But really, none of the math changes, and that's done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And that's why I fundamentally wrote micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later. Okay, so here's the fun part. My claim is that micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that micrograd would be a very complex piece of code, and
No.
that turns out to not be the case. So if we just go to micrograd, and you'll see that there's neural nets, and this is the entire neural nets library on top of micrograd. So engine and nn.py. So the actual backpropagation autograd engine that gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons. And so
Oh, he just goes up in size. Neuron to a set of neurons, which is a layer, to a set of layers, which in this case is an MLP, but really is a network in general.
it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code, and that's all you need to understand neural network training, and everything else is just efficiency. And of course, there's a lot to efficiency, but fundamentally, that's all that's happening. Okay, so now let's dive right in and implement micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic import. that I copy paste.
Let's see. A derivative is a quotient of differentials. And what is a differential? An infinitesimal change to some quantity. So if you had some function, yeah, screw it, just the squaring function. It's extending the idea of slope to shrink down to a single point, taking advantage of the sort of virtual nature of infinitesimals, where around every point there's a whole world of infinitesimals uniquely associated with it. So for example, 2 plus epsilon, where epsilon's infinitesimal, is infinitely close to 2 and to no other value. And by using this, we can take the idea of a slope, which requires 2 points to determine, and reduce it still to 2 points, but in a way it's also just 1, because it's the 2 points at this case, well, would be 2 and 2 plus epsilon.
In every Jupyter notebook always. And let's define a function, a scalar valued function, f of x, as follows. So I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y. And we can call this function, of course, so we can pass in, say, 3.0 and get 20 back.
He uses Safari.
Now, we can also
Cool.
plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola. It's a quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5.
I'll do an even simpler example, although I have to figure out how to define in C++. Okay. I'll need IOStream to print anything out. Int main. No, should call it F. We'll just call it square. Return x dot how of x 2. 44 overloads. Oh, right, semicolons. Let's see. What was that? Is someone on this stream? That's a first. Hi, Eagle26011. Can auto be used in function arguments? Okay, just in the return. Huh, that's handy. Guess I'll just use doubles. Auto out equals square of 2.0. Will it? Oh. Fine. The differential. Usually EPS is what people will write. What is the default type? Float? Okay, double. With the square of 2.0 plus EPS minus the square of 2.0. Divided by EPS. Really, to capture the idea of a two-sided and one-sided derivative or slope, it should be 2.0 plus EPS minus EPS, sorry, minus 2.0. But basically no one will write it that way. Instead, you would just cancel out the redundant input and just let it be EPS. Let's see, print in C++. That's not too bad. Standard cout derivative end line. Let's run it. Clang C++, build and debug. I run C++ and it asks me about OCaml. That's kind of funny. Hi back, Eagle. How'd you find this? This is my first time streaming. So far, fun. Wow, I've been streaming for half an hour. Time flies. Auto is a C++11 extension. Auto not allowed in function return type. What? Well, that looks complicated. I'm increasingly glad I have spaced repetition, since it looks like C++ is going to require it. Auto type specifier is C++. Okay, well, I thought I was using that. Ah, thank you. Well, yes, I would like to configure the project. Except I don't have CMake tools. That it allows you to show on the left or the right is funny to me. I prefer it on the right. Code folding, database, path. Ah, I like to live on the bleeding edge. Maybe C++23 is a bit too bleeding edge, but whatever. Okay, that's enough setting. Try running this again. Oh, I have to restart it. Not getting a squiggly, so that's a good sign. Oh wait, I don't want to build the G++. Hmm. Okay. Code runner. How to use it. Okay. What's the arg? CLI arg or C++. Standard equals. Okay. C++ 20, then it is. Okay. It gives that the output is 4, and the derivative of x squared at the value 2 is 4, since the derivative at any point x is 2x. So plug in 2. If I set x to be even smaller, then the approximation will typically get better. Yeah, there. Do I need to put auto?
In steps of 0.25. So axis is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on axis. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get a nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative? 5
Yeah, I'm
expression
gonna
and
skip
see.
this part.
Definition of derivation. Limit as h goes, what it's saying is if you slightly bump up, you're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by a small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in 0.3.0. So we can look at f of x, of course, is 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much is telling you the sort of the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded in the positive direction. And we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope, because we have to make h very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer because we're using floating point arithmetic, and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it. So the function would be 3. Positive direction, the function does complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable d.
That's funny. The word complexification has a different meaning in math, which is taking a real variable and extending it to the complex plane, or the plane. Ugh. I prefer the word complicate. Since it is complicated, you're making it more complicated. And they have the same etymology. The com is with, and the plex or ple is essentially the word for plating or binding rope together.
That is a function of 3 scalar inputs, a, b, and c. So a, b, and c are some specific values, 3 inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c, and think through, again, just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point.
Oh, this is an interesting point. When you're taking partial derivatives, you could use the same h for all of them, but this is technically a mistake. I think you'd call it the perturbation confusion, because all the infinitesimals are supposed to be independent.
Point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h, and then we'll get d2 to be the exact same function. And now we're going to
Okay, I'm now getting lazy with naming. Yeah, it'll be scalar valued, where I just add together the squares. Does C++ have an exponentiation operator? Non-exponential. Does not. Damn. Can this be overloaded in a way that's not horrible? Not for primitive types. Yeah, that sucks. Not going to do that. Let's see if I can define. Actually, I might as well just make F's a constant because I keep reusing it anyway. Explicit type is missing. Int assumed? That's horrible. Const auto, auto const. There, that's more like it. Actually, I guess all of these can be consts as well, but that's just some complication, so not gonna do that. Let's try this out. Will this work? I guess the regular D could just be the trivial case with the identity function. The C++ have anonymous functions. Lambda expressions. Okay, it has it, but it's ugly. But what else is new? How do overloads work? More than one function of the same name in the same scope. Huh. How do I annotate a function type? function is argument. Pointer standard. Oh, couldn't infer the type of auto. Okay. Fine. Oh, if I try to put a redundant template, it just instantly stops it. That's kind of funny, actually. Does that work? Argument list is missing. How do I alias it? Template type new. Okay. Mostly I'm doing this because I really dislike typing. Double. And F will just take in one type as well. Oh, oops. Should be next. Expected expression and no matching function for. Okay, the no matching just comes from this. use function in parts. Takes one. Oh, there's no comma. Function cannot return function type. Okay, if I just do this and not be clever with it. Okay, if I make it the double. Okay. And now let me try this. What does standard identity do? And how is it? Oh crap, I forgot to get an it. Info.plist. Gross. First commit. Okay, let's try the partial derivatives.
To print,
Wait, why am I looking at his? Let's see if I want the partials. I can just perturb each one of the input arguments directly. I wonder if there's a way to do D with partials. So I have some function that takes an arbitrary number of doubles and then the doubles in question, and then differentiates with respect to each of them. There's also the total derivative, which is essentially the sum of the partials. The notation for it is slightly confusing since, for example, if you have, say, a function of two arguments, a and b, and the function is called f, then the total derivative of f would be partial f partial a times dA plus partial f partial b times dB. And if you cancel out the dB, dAs, and the lower partials in the denominators, it looks like dF is equal to dF plus dF. So it looks like it's equal to twice itself. And yet isn't zero, which is a contradiction. But that's because the Leibniz notation doesn't work as well. There's a paper on this somewhere. I think it's like differentiables as algebraically manipulable entities. But let's just take partial A. Does C++ have tuples? Somehow I doubt it. I don't think it has tuple unpacking either. Unpacking a fixed size container can be tedious. Okay, never mind. Minus G of A, B, C. All over X. I should actually print it out too. All right, DGDA. Let's do DGDB then. Having divisions sure is useful. So you could extend this in a vector space by constructing its Clifford algebra and then dividing by some invertible multivector, which would probably just be a simple k vector. Command Shift Y opens debug console. Okay, is the partial derivative 6? Yes, it is. Standard make tuple. Gross. Okay, then can I do this? I can see why you wouldn't do this though, given that it looks awful. Seems to fuck with type inference. What if I make it an array? Doesn't seem to work. Maybe if I do standard array 3. That's double. And I did in the wrong order. Invalid specifier for structured binding. Okay. Cool. Learning C++ in this piecemeal way isn't fully satisfying, but I'm following Karpathy's advice here to go depth first rather than breadth first, only learning what you need as you need it, since it goes against my typical tendency.
F1, D1 is D1, D2 is D2, increased by H. B is minus 3, C is 10. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but B is a negative number. So if A is slightly more positive, because B is negative 3, we're actually going to be adding less to D. So you'd actually expect that the value of the function will go down. So let's just see this. Yeah, and so we went from 4 to 3.9996. And that tells you that the slope will be negative, and then d by b addition and y at which. Okay, so we now have some intuitive sense of what this derivative is telling you about the function. And we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to build out this value object that I showed you in the README page of Micrograd. So let me copy paste a skeleton of the first very simple value object. So class value takes a single scalar value that it wraps and keeps track of, and that's it. So
Let's see. Is it class or struct? Default accessibility. Any other differences? What does the colon mean? spam callers. Does that work? Do I even need to return them? Okay, how to print it? Oh, that's cute. A friend. Okay, let's try this out. Constructor creates a delegation cycle. Oh, and semicolon. Constructor should not return a value. Oh, that's easy. Okay. Okay, good.
We can, for example, do value of 2.0, and then we can we can look at its content. And Python will internally use the repr function to return this string. Whoops, like that, just like two. So currently you would get an error because Python doesn't know how to add two value objects. So we have to tell it. So here's addition. So you have to basically use these special double underscore methods in Python to define these operators for these objects. So if we call if we use this plus operator, Python will internally call a dot add of b. That's what will happen internally. And so b will be the other, and self will be a. And so we see that what we're going to return is a new value object, and it's just it's going to be wrapping the plus of their data. But remember now, because data is the actual like numbered Python number, so this operator.
I still have a habit of using Google to look up info after, God, how many years of that? Operator plus. Okay. Oh, oops. Okay, while we're at it, what are the operators? Plus, times, subtraction, negation, unary minus. Okay. That seems false. This is the kind of thing that I would want to use some abstraction for, like apply, but no, not today. So does operator minus? Okay, the other one is the right operand. And for later, if it's ever not commutative, not taking any chances. I don't think I need to overload division while we're here. Any other operators?
Here is just the typical floating point plus addition now. It's not an addition of value objects. And will return a new value. So now a plus b should work, and it should print value of -1, because that's 2 plus minus 3. There we go. Okay, let's now implement multiply, just so we can recreate this expression here. So multiply, I think it won't surprise you, will be fairly similar. Then it's just that you'll get some kind of an ugly we are, to do mul and add that gave us as well. The connective tissue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how
Okay. How long have I been streaming? 2 hours. Okay, I'm going to take a break soon.